Hey, I'm Courtney Waterman, your tutor. Lover of anime, manga, and math. And you just tuned into another session of Tutor Me Sempai.
Welcome back, everyone. Today we're jumping into a 12th grade topic, the Squeeze Theorem, also known as the Sandwich Theorem. Now, if you're new to my channel, I'll be putting timecodes in for this video in the description box below, so use it to skip ahead to whatever part of the video you think is most interesting. As always, if you have any questions about what we see today or even your own homework, you can always put in the comment box below or visit my Facebook page at Tutor Me Sempai and tell me all about it there. At the end of this video, I've been linking my 12th grade playlist, so if you're interested in that, make sure you stay tuned. This video is only going to have 3 parts, so leave a like, smash the subscribe button, and let's get started! Now, the Squeeze Theorem is going to be a very powerful tool that can help us out in many pinches. However, it's not going to be used in all situations, and you'll see exactly why I say that in just a moment. But when you can use it, it's going to be super helpful. So how does it work? Well, let's say we have a function f of x, and we know that this function f of x is bounded by 2 functions. So its upper bound is, let's say, g of x, and its lower bound is, let's say, h of x. We know that it's always going to be between these 2 functions, always greater than or equal to h of x, and always less than or equal to g of x. If we know this to be true, our Squeeze Theorem tells us that if we know the following to also be true, let's say the limit as x goes to some a of h of x equals the limit as x goes to a of g of x, if we know this to be true, it equals some L, but they're equal to each other. The Squeeze Theorem tells us that we also know that the limit of our f of x, our middle function, as x goes to that same a, has to be L as well. So if your function is bounded, if you have 2 functions that bound your function, 2 other functions that bound your function, and you know that the limit as x goes to a of both bounds equal each other, your Squeeze Theorem lets you know that your inside function, your original f of x, has to also have that same limit. This is why it's super powerful. If you can get this to work, then great. However, it also shows you its limitations. You have 2 things you have to make sure you have before you can use the Squeeze Theorem. You have to find bounds, and you have to make sure that those bounds have limits that equal each other when you approach the same a. Without either one of those 2, you can't use the Squeeze Theorem. So you're not going to use this for all of your limits. However, there are some limits that you will be able to use this for, and it will save you a lot of headache. For those who learn a little bit better with visuals, here's a quick visual on how it works as well. We have 3 functions here, and you see that your brown function, your f of x, is bounded between your blue and your green. Green is always going to be greater, blue is always going to be less than, except where they're equal. And you see that when you have the limit of h of x and g of x at a particular point being the same, it squeezes your middle function to have that same limit. This is why it's called the Squeeze Theorem or the Sandwich Theorem. You're sandwiching your middle function in between your top and your bottom functions, forcing it to have the same limit. So if you know that they're bounded, right? Let's say over here, if this is your function here, right? You don't have this other part. This is your function here. It's bounded top and bottom by an h of x and a g of x. However, you see that h of x and g of x don't have the same limit. That means you can't use the Squeeze Theorem. You have to make sure that it's bounded and that both limits are going to be the same for your bounds. If you have both, feel free to use that Squeeze Theorem. So now we know how it works, let's try this out on a rather generic example. Let's say we have this function f of x. It's some generic f of x, but we know something about this f of x. We know that it's always going to be bounded by 5 and x squared plus 6x minus 2 in this fashion. Always, all of its values are going to be between these 2 bounds. However, we need to find what the limit of f of x is going to be when x approaches 1. Now you may be looking at this like, we don't even know what the actual function is. It doesn't matter. We can use our Squeeze Theorem to still find this generic limit. And I've already given you the first part. You have your bounds. Now you need to check your second part. Remember, it's not enough to just have the bounds. The bounds are great, and it's a great first step, but we need to know that what? The limit for the bounds, as x goes to the same 1 here now, is going to be the same. So let's figure this out. What's the limit as x goes to 1 of 5, and what's the limit as x goes to 1 of x squared plus 6x minus 2. Well, we've talked about both of these on this channel before. If you missed those videos, no worries, you can find them both right up here. However, this we talked about to be always 5, right? Your constant, the limit, is always going to be whatever that constant was. The constant function doesn't change. So you can just simply write that out. And we know this is going to be plugging in our 1 everywhere there's an x. So we have a 1 squared plus 6 times 1 minus a 2. And this is going to be 7 minus 2, which equals 5. So the limit of 5, we know to be 5, the limit of x squared plus 6x minus 2 as x goes to 1 happens to be 5 as well. So the limit of our bounds are both 5. What does that mean? Well, it means that the limit of our function that is always going to be between these two functions, our function f of x, has to also be 5 because we're squeezing f of x between these two. So as they both go to 5, it has to go to 5 as well, or else this is not true. So this is how you use the squeeze theorem even if you don't know what the function is. It doesn't matter. What's most important are the bounds and how their limits relate to each other. If you're bounded and your limits for your bounds are the same, then just simply find what the limits are for your bounds, and that's going to be the limit for your function. So in this example, I gave you the bounds. Let's try one more example, a little bit more involved than this, in which we have to find our own bounds. Let's say we have an example that looks a little something like this. Now, this looks a little scary. We have the limit of x to the 4th times sine of 7 over x as x goes to 0. This looks pretty daunting. Now, if we try to just plug in our zeros, we would get what? 0 times sine of 7 over 0, which, what does that go to? That doesn't exist. We can't even do that. So how do we find this limit if we can't just plug it in? Well, it happens to be in this video, so let's try using our squeeze theorem. But we don't know the bounds. How is this bounded? Do we even know if this is bounded? Well, let's first start with an easier version of our function. And then let's work until we get this. We're going to work it up until we get this. So let's first start with, let's say, sine of x. A very simple sine of x. Does sine of x have bounds? Yes. We know that sine of x is going to be bounded by 1 and -1. It's always going to be oscillating between 1 and -1. This is the first step. We know that this is going to be bounded. However, this sine of x is not this, right? We have a little bit more work to do. So if we start here, and we know this to be true, if I was to say this, well, for every x, this is going to be true. That means this should also be true, of course, where x is not 0, right? For every value that's in sine, this is true. So wherever x is not 0, this is defined. Therefore, this should be the same as that, right? We have sine of x, and now we have sine of 7 over x. But it still has bounds between -1 and 1. Now, I hope that makes sense, how we got from here to here. This is pretty much the same exact thing. You're just saying that whatever this is also going to be true because this is true for every x. This just can't be 0 because that's not defined there. But as long as this is not 0, this is going to be the same as this. So now that we have this, we're a little bit closer to what we have here. However, we're not quite there. We're not quite there. We have a little bit more to do. So what do we need to do in order to get this looking like this? We already have sine of 7 over x, but we are missing what? Our x to the 4th. So let's multiply everything by x to the 4th. So if we did that, we're going to get a negative x to the 4th less than or equal to our x to the 4th sine of 7 over x less than or equal to x to the fourth. Now we have new bounds for this function, which is our original function, right? We have bounds now. We found the bounds. But are we done? No. In order to use our squeeze theorem, yes, it's important to have our bounds, but we should also figure out what the limits are for these bounds and make sure they're equal. So what's the limit of negative x to the fourth as x goes to 0? And what's the limit as x goes to 0 of positive x to the fourth? Well, if you're plugging in your 0, it doesn't matter if it's negative or raised to some power. This is going to be 0, and this also is going to be 0. So it means that the limits for both of these are in fact equal, and they both equal 0. So if we know that the limit of negative x to the fourth as x goes to 0 is going to squeeze this limit, x to the fourth sine of 7 over x, which is squeezed by this limit as x to the fourth. If we know this to be true, then we know by our squeeze theorem that this has to be 0 as well. So no matter how ugly that got, because you knew your bounds and we had to build it up, you might not be able to find your bounds immediately when looking at this. But if you can build it up like this, then you can find the limit of your bounds. And if they are equal, then you already know the answer to your question. The trick is finding your bounds. If you're not giving your bounds like we were in the previous example, you're gonna have to start somewhere. And if you have something like this with a trig, then that might be a sign of where you should start. If you have a sine, start here. If you have a cosine, start with cosine. It has the same bounds. After you get your bounds, try to manipulate what you have until you get this again. So we didn't start here, we started at a regular sine, and then we slowly started manipulating it until we got to our original function. That's how you find your bounds and use your squeeze theorem to find your limit. So I hope you were able to follow along with today's video, and hope you now understand how you can use your squeeze theorem or your sandwich theorem to find your limits. However, if you have any questions about what we said today, or even your own homework, you can always put in the comment box below, or visit my Facebook page at Tutor Me Sempai and tell me all about it there. If you hadn't done so already, remember to leave that like. It surely helps the channel by letting YouTube know that you found a video helpful. And if you found a video helpful, so can someone else. So leave a like, hit the notification bell, smash the subscribe button, and share this video with a friend. Well, that's all the time I have for today. I'm really hoping this helped with your homework. I'm looking forward to seeing you again next week. I'm Courtney. Here's your playlist, and this has been another session of Tutor Me Sempai.